Alrighty, so in the past few lessons, we've talked about how to make your own schematic, find your components, and specifically run a steady state analysis using DC sources. Now we'll be going over how we can actually view changes with our circuit with respect to time, whether we have a changing output or whether there's just something we like to see that varies throughout time. And we're going to be doing that with two things. One, a transient simulation to view how it changes over time, and the 555 timer to generate a really nice periodic output that we can easily measure. And to find this 555 timer, I'm going to go to draft components, and I'm simply going to type in any 555, and it should pop up just like this. Hit enter, zoom in a bit, place it anywhere you want. I'm going to place it in the middle, and I'm just simply going to make the circuit. And a big part of why at least I'm using a 555 timer is because I find that it's relatively easy to view nice periodic outputs using this 555 timer. And I'm just placing down some passive components using the same shortcuts. And now it's time to do some basic connecting. So I always like to try to line them up as much as I can to get really easy, I guess, routes for the circuit. And I'm just doing some basic connections here. Connecting ground to ground. And now I'm going to be overlapping some components. Like so. And I'm just missing the discharge and the power. Zoom in a bit, sorry. And so one thing I do want to highlight is that when you have overlapping wires, note that if you don't see a box, then that means they're not connected. They're just on top of each other. It makes readability a bit hard, and I probably could have wired it a bit better, but I did want to show what happens when you have overlapping wires that aren't connected. So you're not going to see a box, and that just means that they're not connected. And we can prove this by simply dragging the wire of the trigger up and down and see that the wire from out and reset aren't moving, so they're not connected. Just something to keep in mind. And if you can route your wires in such a way that these don't overlap, then all the better. All right, so now we're going to be putting some values for our components. I'm going to be right-clicking this capacitor, giving the value of 0.1 U microfarads, giving this pull-up resistor a value of 1 kilo ohm. And I'm going to make R1 and R2 values that give the output of this 555 timer a duty cycle of about, I would say, close to 60, 66%. I'm not sure the exact value. I think it's around that ballpark. And giving this voltage source value 5 volts. All right, so this is our basic 555 timer circuit that I essentially built from following the Texas Instruments spec sheet for the NE555. And it's set to run on an astable mode where it's going to put out periodic square waves, which are dictated by essentially the RC values here. Now, how do we actually view it? So we're gonna run a transient simulation, which is denoted by this syntax .tranx, where x is in seconds. And when you say x, you're essentially saying that I want to run my simulation from 0 to x seconds. And as you can imagine with the prefixes, you can also have prefixes for this. So prefixes and all the prefixes apply, like XU for microseconds, XM for milliseconds, and just X if you want regular seconds. It's important to choose a time range that allows you to properly view your circuit. So let's say you're viewing at a really fast frequency, like 1 megahertz. Running it at 1 second is going to give you, I would say, maybe not as clear-cut data as it would from a really, really low time frame, maybe even in the 1 microsecond range, excuse me. So something to keep in mind is that you need to choose the proper time range for your circuit. And because I know the output frequency of this 555 timer I built, I know that I can simply run it at half a second and it'll be fine. But for your application, just make sure that you're choosing the right time range for your circuit. So I'm going to go to my SPICE directive by pressing S, typing in .tran, and I want to run it at 0.5. So I'm going to type 0.5. Place it anywhere. And then I'm going to run the circuit. So I'm going to hit the running man, or I can right click and then hit the running man. And then now I want to view the output of this circuit. So I'm going to hover over, I'm going to do that again. I'm going to hover over the node I want to view the output of until I see this red probe, and red probe denotes voltage. So I'm measuring voltage here. And I'm measuring the output voltage. So by measuring the output voltage, I click on it, and then I get this nice, pretty waveform plot of a square wave. As you can see, it's about 66% duty cycle at a nice viewing range because I chose a correct time range for this. And if I want to view more voltage nodes, I can hover over any node I want until I see this red probe. So let's look at the capacitor. Click on it, and then here we can see this nice capacitive waveform as well. So that's how you view voltages, but you can also view currents. So let's say you're hovering over a component. Now this time you hover over the component directly, not the node, the component directly until you see this black circle, usually with a red arrow, and that simply denotes current. So the black circle denotes current. And now we can see the current through the resistor. All right, so now back to here. Now let's say we wanted to do something similar to our .op measurement, where we're taking a differential measurement. So we're taking the measurement of something relative to something else. And we can do that by simply going over the node that we want to measure. So the voltage in this case that we want to measure, click on it and hold, and now move to our relative point. So this to our second differential measurement. In this case, I want to measure it relative to the output, and I'm going to let go. And as you can see, I'm now taking the differential. I'm now taking a voltage measurement of the capacitor, of the voltage across the capacitor, relative to the output node of this chip. So overall, the principles of the OP analysis and how you can kind of take voltage measurements stay the same. The syntax for transient simulation is different, but you can also view currents and voltages just the same. So that's how you view time varying circuits. And now and then the next few lessons, we're going to be looking at how we can actually use these time varying simulations to view other types of circuits, along with making our own time varying simulations.